Today's background is from Kiandra in the Snowy Mountains, and looking at the background, you might go, "Well, hang on, you're just looking at an open field," and you'd be absolutely right. So Kiandra was a town from the 1860s that was basically a gold mining town, and it died sometime after when people stopped being interested in gold there. And up until they built Cabramurra for the Snowy Mountains project in, I think, 1940s or 1950s, this was actually the highest town in Australia at 1,400 meters or so. Anyway, there's not much left of Kiandra, and particularly so after the bushfires at the start of 2020, when the few things that did remain of Kiandra kind of got very badly burnt. But if you're ever on the Snowy Mountains Highway on the road from sort of Adaminaby through to Tumut, it's a really nice drive to take, and really interesting to see how the high country is very different from lots of other parts of Australia. All right, so in this second half, what I want to do is take my Cauchy-Schwarz inequality, and let me bring up some slides. I want to get what we call the general uncertainty principle. And it's general in the sense that it holds for any two observables that I deal with in quantum mechanics, not just, for example, position and momentum or energy and time, okay? It has a form that looks like this. L and M are our two observables and the operators corresponding to them. And you can see there's an uncertainty on the left. And on the right, we have something that basically looks like a commutator bracket, like what we saw in lecture 10. So where I'm going to go in this is basically start with my Cauchy-Schwarz inequality from the first half, put in some actual vectors for that, and then basically work my way through to getting myself this form of the uncertainty principle at the top. And then once we have that, we'll put P and X in, and I'll show you that you get the Heisenberg uncertainty principle out. So let's bring up some paper so we can start on this. What we're going to do is start out by taking, you'll remember in the last lecture we had our Cauchy-Schwarz inequality. It looks like this. Inner product of A and A times the inner product of B and B is greater than or equal to the inner product A, B. Like so, okay? And the absolute value sign that we're carrying in there is basically just something we keep in order for handling the fact that we're dealing with complex vectors. We need to take care of conjugates at some point, okay? So you'll remember earlier on what we could do was define measurement in quantum mechanics as operating the operator on a state to get a new state, okay? So what we can do now is basically define our ket A as the state vector that comes about after you make the observation or measurement of L. So it would be L times some starting state psi. And of course, we can now define our B in the same way with our other observable that we want to observe simultaneously, which is M. Okay, so what we would do here is call B to be M times psi. Okay, quick word of warning just here. If you have a look, if you happen to be working through Susskind's book, you'll notice that Susskind's book at this point actually defines B with an I in front of it and A without an I in front of it. Just to explain what's going on there, Susskind doesn't want to have to deal with two little pieces of complex analysis that we'll take care of in a second. So to avoid that, what he's actually doing is pulling a little bit of a fudge or a sleight of hand and introducing an I in front of the M because he needs to get an I later, okay? I actually don't like that version because ultimately what you're doing is taking, you know, your ket A and your ket B and somehow treating one of the two measurements to be different from the starting position so that you can get your right answer. I generally don't like fudges in any books, so I usually try to hunt them down ruthlessly and then rip them out, and that's what I'm going to do here today. So I'm going to take a slightly different path to Susskind and do this the right way. There's two things that we need to know if we're going to do that from your complex analysis courses. I'm not going to go through and prove them because this is a physics course, not a maths course. I'm just going to put them down, and if you don't believe me, you can go back and have a look at them, okay? So the first thing that we need to know from our complex maths courses is that if we take some complex number z and we take the square of the magnitude of it, bear in mind that z is now a complex number, so we have to worry about conjugates, which is why we've got the absolute value sign in there. It's going to be equal to the square of the real component plus the square of the imaginary component, right? This is just a decomposition of any arbitrary complex number into its real and imaginary parts. So what we would have here is real z squared plus imaginary z squared, okay? And so you could think about this in terms of an Argonne diagram where you've got your real axis and your complex axis, and those add together to give you your arbitrary z, which points in some direction that's basically just the sum of your real part and your imaginary part. Okay, we all know that. Now we can pull this same trick that we talked about in the first lecture with inequalities. What we can do is basically just go, well, we can always just replace it with something smaller. Okay, so what we can do is say here that the length of z squared, it's going to be equal to the real plus the imaginary part. And the real part, when you square it, because now you're taking a square, you have to have a positive number, it's always going to be bigger than 0, okay? The smallest it can possibly be is 0, in which case z squared is equal to the imaginary of z squared. Or if the real part is non-zero, then it's always going to be bigger, right? So what we can do is write in here the imaginary part of z squared, okay? And that's because real z has to be greater than or equal to 0 because you're taking the square and therefore it must be a positive number. Okay, so this is the first thing that we kind of need to know from complex maths to get through here. And usually you've learned that fairly early in your complex maths courses. The second thing we need here is to know that the imaginary of z is able to be written as z minus the conjugate of z divided by 2i, okay? Z minus z star on 2i. And this is something you learn pretty quickly when you're doing complex maths courses. And so if you're not sure of this one, you can check it for yourself. You can either prove it for yourself or you can just put some random complex number in there and verify that it actually behaves exactly that way. So these are the two things we need. So let's now go back and to our Cauchy-Schwarz inequality, which I'll call equation 1. And so let me just rename these things as A and B so we don't get tangled up in what we're referring to here, okay? So we're going to start from 1. And what we're going to do is go that inner product of A and A times the inner product of B and B has to be greater than or equal to AB squared. And of course, we know from our first thing about real numbers, first thing about complex numbers up here, that we can replace any complex number with the square of the imaginary, right? So what we can do is go down here and go, I'm going to have imaginary of the inner product of A and B squared, okay? That's the first step. Then what I can do is take any imaginary. So what I'm going to do is actually use my item B here. And I can write that item B as the difference between the thing and its conjugate divided by 2i, of course. And of course, if we take an inner product, when we take the conjugate of the inner product, we just reverse the order of the two terms, okay? So what we can write this as is greater than or equal to 1 over 2i, we just pull that out the front, times z, which will be AB, inner product of A and B, AB, minus z star. So take the conjugate, reverse the two labels here. So this is B and A. And then the whole thing is squared, okay? All right, so now what we can do is, substitute in our ket A and ket B. Okay, so now what we're doing is basically just saying, let's drop our measurement in. So what we would have here is basically, if I think back up to here, if I want the bra for A, what I need to do is take the conjugate of the operator L and the bra for psi. So it will be psi L conjugate. Okay, and you remember that we put the operators on the long bracket side when we write this, so that's why we've swapped the order here, times A, okay? And of course, A will be L times my state psi. And I can do the same thing for B, so I've got now bra of psi times M conjugate. M psi is going to be greater than or equal to my 1 over 2i, I can always write as minus I over 2. And again, this is one of these things that if you do enough complex maths, you start to realize how to convert these things very, very quickly. The people who are practiced just boom, 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 boom. The people who aren't have all sorts of funny things going on, and it makes life harder. We can now put our inner products in over on the right-hand side here as well. So we would have psi L conjugate M psi minus psi, I'm going to have to pull this over a little bit, M conjugate L psi, running out of edge here, squared, like so, okay? Need to write a little narrower, I think, just to get this in. Okay, so we got all this here. At the moment, you'll be going, hang on a second, aren't L and M Hermitian? Yes, they absolutely are in everything we do in quantum mechanics. So we know that L dagger is equal to L and M dagger is equal to M. So we can go through and do that everywhere all the way through here, right? So what we would have is psi, L and L is L squared, psi. M dagger and M becomes MM, and M is M squared. So we've got psi M squared psi just here. This is greater than or equal to. We keep our minus I on 2 out the front, and then missing a bracket just in here. And then we can collapse these terms on the far end as well. So this would now be psi Lm psi minus psi Ml psi close squared. Okay, like so. And so already you can see on the right-hand side, we're starting to get something that looks a little bit like a commutator in here. So feeling a little bit comfortable about this. You'll remember that these things here are basically expectation values. Same over here, right? So we can write this in a form where we're really just dealing with expectation values. We've got the expectation value of L squared times the expectation value of M squared is greater than or equal to minus I on 2. Now, what we're going to do here is actually pull these two things together before we do the expectation value on the right-hand side. So what we would have is psi times Lm minus Ml psi on the right-hand side, like so. And then we can pull that into a commutator, minus I on 2, psi, let's write our commutator, L comma M. And then the last step in here would be to write our expectation value. So this would now be minus I on 2, expectation value of the commutator L comma M squared. Okay, so now we're very close. Now what we need to do is pull out a result that we had from lecture 11, which was the whole point of lecture 11 in the end, which is that if our distribution has 0 mean, right, then what we know is that the expectation value of L squared is equal to the uncertainty of L squared, and the expectation value of M squared is going to be equal to the square of the uncertainty in M, like so, okay? For zero mean for both those two functions. And you'll remember way back, what we also had to prove was that that uncertainty doesn't change when we shift the function away from zero mean, okay? So this result also holds like so, okay? And if you really wanted to, you could go through and do that algebra explicitly, but we can basically just rely on the fact that we know how this behaves under shifting to give ourselves an easy ride, so to speak, by just treating the result where the mean is zero to keep the maths easy, and then know that we can shift that across and everything is well behaved. So now you kind of see the point behind the last lecture. I'm setting myself up for an easy step at this point. So what I want to do is take that now and use it in the relation that I've got above that's really just coming from my Cauchy-Schwarz inequality. So we can replace these two terms here with the relative, with the corresponding uncertainties. So this will be now the delta L squared, delta M squared is greater than or equal to minus I on 2 expectation value of L comma M squared. And of course, I can take the square root of both sides, right? And I know that I'm still going to hold my inequality in this particular case. So what we have here is basically delta L, delta M is greater than or equal to when we take the square root to keep everything well behaved, we're going to take the absolute value, okay, just in here. So minus I on 2, because otherwise we don't want something to pop out that's complex, okay? So we'll restrict ourselves to that, L comma M, like so. Okay, and this, of course, is our final result. You'll notice that on the slide, there's no minus sign, and on my notes page, there's a minus sign. Ultimately, the absolute value on the end takes care of that minus sign. So if you look through books, some will have the minus, some will not have the minus. No one really cares because ultimately it's taken care of by the absolute value that we imposed when we took the square root to keep things behaving in a real way, right? We can't have complex uncertainties. So we basically just restrict our uncertainties to be real by putting that absolute value sign in. So you'll see both forms floating around. Sometimes you'll even see it written with 1 over 2i still. All of those forms are exactly the same. They're just slightly rewritten versions of the same thing, dealing with the complex nature of this thing in slightly different ways. Okay, so that's our general uncertainty principle, and it holds for any two observables that you want in quantum mechanics. If the commutator is equal to 0 in that particular case, then the expectation value of the commutator will be 0, and that whole term on the right-hand side collapses. What that means is delta L, delta M is greater than or equal to 0, and in that particular case, you can actually measure those two observables with absolute certainty simultaneously, okay? And there's whole piles of cases where this is true. So for example, if you measure position X and momentum not in the X direction, but in the Y direction, I'll let you do this one for yourself because it's a nice exercise. You go through, you take X, you get the commutator, but now using the PY operator. So it would be minus IH bar d over dy. If you work through the same logic you did before to get the commutator, now the commutator is 0, not IH bar. And if you put that into here, then you find out that you can measure with absolute certainty position X and momentum in the Y direction with no problem at all, okay? What I want to do to finish off this half of the lecture is show that if I measure position X and momentum along X, right, then the commutator that we got back in lecture 10 actually gives us an uncertainty here that is not 0, okay? And this is where the Heisenberg uncertainty principle comes from. So let's go through and do this. what we're really doing here is taking our operator L and making it the operator X. I'll put a little hat on it so that we know that we're talking about the operator here. And our observable M, we're going to make it P of X, okay? And you'll remember that X hat was just X and P hat was minus I H bar D on dx. Okay, and I usually write that as a partial because if we are considering y, then it really is a partial derivative rather than a absolute derivative. Okay, so we can more or less just pop straight down to the next line and plonk everything into the right place. So delta x, delta p of x is going to be greater than or equal to absolute value. Doesn't matter whether I have the minus here or not. Let me put it in just to be consistent with what I've got written up the page. If you have a look at my written notes, you'll notice I've dropped it because it's not that important. So I over 2, expectation value of x and p in our commutator here. So just replacing L with x and m with p of x. Let me just put a p of x in there just to be really clear. Of course, we got this commutator in lecture 10. So we know that commutator of x and p of x is equal to I h bar. And you can convince yourselves that if you swap these two operators, you now get a minus sign, and the minus sign kicks on through this thing. So again, this is why we don't really care about the minus sign inside this absolute value, because there's not just a minus sign that's sometimes attached here, but there's also a minus sign that comes about from the order of the two operators you put in the commutator, and that shouldn't be meaningful in this particular case to extracting out uncertainties, which is just a number for the two, a relationship for the two particular things that you're trying to observe in here, okay? So this thing would now be, let's take this term down here, delta x, delta p of x is going to be, we can write this term here. Then we've got psi. In the middle now would be our commutator, which has now become IH bar. Here on the right-hand side would be our state psi. Okay, so all we've done is just gone from an expectation value out to writing what the expectation value is in full bracket notation. And one thing to be careful of in here is that sometimes actually the commutator of two operators is another operator, okay? And so you have to be careful, or at least cognizant of the fact that sometimes what you're doing with this expectation value over here is actually getting the expectation value for another operator. If you want an example of that, use your Pauli spin matrices in this part of the problem. Try that for yourself, and you'll see that actually what you get is the expectation value of another operator inside this uncertainty principle. It's a really interesting exercise to do. And I'll do that one and put that up in my notes as well. And one thing to be careful of is that's not equals, that's greater than or equal to. Okay, so then next step in here, what we can do is just pull the IH bar out the front, right? So this will be minus I on 2 IH bar psi times psi. And of course, this thing here is just 1, right? Just by normalization. We can clean up the I squared in here. So this thing will end up being greater than or equal to I times I is minus 1 times the minus gives us a plus. So this will be H bar over 2, like so. And then at this point, we can clean up the absolute value signs. So here we've got H bar over 2. And sure enough, you've got your classic Heisenberg uncertainty principle popping out of here, okay? So there's really nothing magical about Heisenberg's uncertainty principle. Ultimately, all it is a requirement. It's something that pops out of the maths once we impose the requirement that we're working in a vector space, and this vector space is geometrically sensible. And what I mean by geometrically sensible is that lengths have meaning, and if we make shapes like triangles, we can work out that certain combinations of the edges are bigger than other combinations in some way. So really, uncertainty principle is just an axiomatic outcome of the maths that governs the world we live in. There's nothing really magical about this. And when you realize that, quantum mechanics actually becomes nice. It's another one of these things that people try to attach some weirdness or some mysticism to, that ultimately is just an outcome of, we live in a world where maths works the way maths works, and here is the physical outcome of that happening. This is the end of my half of the course, unless you watch the optional lecture I'll do later on quantum computing. And so where you'll go next in the second half of this course with Peter is to start looking at this idea of a particle traveling with some position and momentum, looking at it from the framework of Schrodinger's equation and wave functions a little bit, just to get sort of that idea of the functional side of quantum mechanics together, and ultimately start looking at momentum and position as two quantities that are linked via Fourier transforms, which is actually quite interesting because it also generates you the same uncertainty principle that we got today, but as a mathematical axiom of how Fourier series work. I'll leave that to Peter. I hope you've enjoyed my half of the course, and maybe I'll catch some of you at some point in the future. Cheers.